In this segment, we're going to review the background and some of the basic equations behind the nuclear magnetic resonance experiment. We're all familiar with this as chemists. We know that the NMR can give us very valuable information about a chemical sample because the spectrum is showing signals from all of the unique nuclei that are present. So it gives lots of structural information, and we can follow what the electrons are doing because the position, or where the peaks occur in the spectrum, is directly due to what the electrons are doing in the vicinity of the nuclei. It is a nuclear property, though, that we're measuring here. The nucleus itself of any atom has an intrinsic spin angular momentum, just like electrons. Remember, we studied those equations in first semester P-Chem. Electrons can be spin up or spin down, and there are vector equations that govern this from a quantum mechanical perspective. The boxed equation shown here shows how that works for nuclei. Unlike electrons, though, you can have something other than a spin 1/2 value for a given nucleus. So let's see how all of this works. There is something called the spin quantum number, which is a property of a given nucleus that can take on different values. Accordingly, then, the eigenvalue of the spin squared operator will take on different values according to the formula shown here in this box. The projection of that vector onto the z-axis can take on integer values that go from -i to +i in steps of 1. So think of the case of the spin of a nucleus as being just like a vector that's spinning about the z-axis. We know from these quantum mechanical equations in the box, we know what the length of that vector is from the first equation, and we know its projection onto one of the axes from the second equation. But the other two projections are unknown, and so you can think of a nucleus as spinning in this way, spinning around the z-axis. Let's look at the different values possible for the spin quantum number with some examples. First of all, we can categorize nuclei into several different types according to their atomic number and mass number. If you have an even atomic number and an even mass number, the spin quantum number will be 0. And this is the case for nuclei that cannot be used in the NMR experiment because there is no quantity or no property for the magnet to interact with. So essentially those nuclei look the same whether they're in a magnet or not. So any atom that has an atomic number that's even and a mass number that's even will have a 0 quantum number for the spin. If you look at odd atomic numbers and even mass numbers, then you start to get nuclei that can be seen in the NMR. And their spin quantum numbers will all be integers. They have different values depending on the example. Now the third and final case is if you have an odd mass number. If you have an odd mass number, it doesn't matter if you have even or odd atomic number, you'll have fractional spin quantum numbers. For example, if you think of the carbon-12 nucleus, carbon-12 is not seen in the NMR. We can't do NMR using carbon-12 atoms because it is an even atomic number. The atomic number of carbon is 6. There are 6 protons. Any nucleus that has an even number of protons will be invisible to the NMR. Here are some spin 1/2 systems: carbon-13, tin 117, phosphorus 31. For all of these cases, you have an odd mass number. You see the mass number is given as an exponent here. These are all odd numbers. Any nucleus that has an odd mass number will have a fractional and non-zero spin quantum number. Nitrogen-14 and deuterium, which is hydrogen-2, these can be seen in the NMR. They have a value of I equals 1. You see they are instances where the atomic number is odd. 1 for hydrogen, 5 for nitrogen, right? But the mass number is even. Boron-11 has a spin 3/2. Germanium-73 has a spin 9/2. Those rules of thumb are just there based on how the nucleus is balanced in terms of the numbers of neutrons and the numbers of protons. So that you become a little more familiar with the equations in the box, I'm going to ask you now to pause the video, try to write out specific equations for the cases of spin 1/2, I equals 1/2, and spin 1. And then you can even draw a little vector model like this showing the different orientations for those two cases. I'll let you do that in the space provided in the handout. And pause the video now, try that out, and then come back and see the answer. Okay, let's look at the results of applying these two specific cases. For the case of I equals 1/2, when we fill in 1/2 for I, we will get 1/2 times 3/2, or 3/4, h bar squared for the spin squared operator. And then for the z projection, the eigenvalue will be plus or minus 1/2 h bar. That means the actual length of this vector for the case of I equals 1/2 will be radical 3/2 h bar. In the case of I equals 1, when we fill in that, we'll get 1 times 2, or 2 h bar squared as the eigenvalue of the spin squared operator. That means the vector length will be radical 2 h bar. And the projection onto the z-axis, there's 3 possibilities there, either minus h bar, 0, or plus h bar. For both of these cases, then, we can diagram those results and think of this picture with the spinning vector around the z-axis. For the case of spin 1/2, there's 2, 1 up, 1 down. And for this case of spin 1, there's 3, 1 up, 1 down, and 1 right in the middle. For each of these spin states, you wouldn't be able to distinguish them outside of the magnetic field. So in the NMR experiment, what we do is we put the sample in a strong magnetic field so that these nuclei will have different energies, and we can do spectroscopy to look at the frequency at which these two spin states change. So the magnitude of that splitting, the amount of energy it takes to flip one of these states into the other, is what we're measuring in the NMR. There are 3 factors that are involved that go into the magnitude of the splitting, and that would be first, the strength of the applied field itself. So the magnet that you're using in the spectrometer, you have different strength magnets, right? So that is going to be directly proportional to the energy gap here. Big magnet, going to be large gap. Little small magnet, very small gap. The second factor is related to the nucleus itself. So there's something called the magneto-gyric ratio of the nucleus, sometimes referred to as the G factor. You have to look that quantity up. Every nucleus has a different G factor, but the bigger the G factor, the bigger the splitting. Finally, the third and this is what we really care about as chemists, but the third factor is, well, what are the electrons doing in the vicinity of the nucleus? They're going to affect this splitting as well. And so that's what makes one atom different than another in a molecule. Even though you have several hydrogen atoms present, if they're unique, they're going to be found in a different part of the spectrum due to this third element, because the electrons are slightly different for those particular nuclei. Add all that together. I'm showing an equation here that has the delta E on one side. Remember, we can express a change in energy as h nu. That's how we can explicitly show the frequency for that transition. H nu is the G factor times the nuclear magneton, just a constant, that's a proportionality constant here, times the field strength itself, B0, and then times this quantity in parentheses, which represents the effect of the electrons in the vicinity of the nucleus. If you wanted to talk about a bare nucleus without any electrons, sigma sub n would be 0, and this term in parentheses would drop out. Here's the value of that constant that's in this equation in terms of joules per Tesla. And if you put this number in, manipulate it so that you have solved for frequency in megahertz, you can come up with this simpler equation that relates any nuclear G factor given the strength of a magnet to where that atom or that nucleus would be seen in the spectrum. And if we put 0 in for sigma, we will get the frequency of the naked atom, the naked nucleus without any electrons, sometimes referred to as the NMR frequency. Let's take a look at some specific nuclei just to see what the G factors would be. Here's a table of nuclear properties. And we see listed in the identity in the first column, but then in the second column, the relative abundance in nature for that particular nucleus. The spin, this is the value of I that we've discussed so far. And then the G factor. And then I'll also include what's the actual magnetogyric ratio. It's the same information as the G factor, but just presented in different units. Look at the proton. That's the first one listed here, a hydrogen 1 nucleus. It's very abundant in nature. It has a spin 1/2 and a G factor of 5. So these characteristics make protons very easy to do NMR with. They are, of course, the first nuclei to be examined in NMR, and they are the easiest. That's because those particular nuclei are present in so much abundance in any sample, and they have a strong G factor. Contrast that with, let's say, carbon-13. The relative abundance of carbon-13 naturally is just a little over 1%. That means very few of the atoms present in our sample have carbon-13. It's a spin 1/2 system just like protons, and it has a G factor of 1.4, so much less than a proton. This is why carbon-13 experiment takes so much longer to run, because we have to enhance the signal to pull out those very few nuclei that are in there that are giving us the signal, plus they are weak nuclei to begin with given the G factor. Now let's turn our attention to how the experiment is conducted. Historically, now this is dating me a little bit because as an undergrad this is the way I did NMR. Historically, we had an instrument where the magnetic field itself was varied and the frequency of radiation was held constant. In other words, you had an electromagnet that you could dial in and change the field, and you could listen then at a particular megahertz frequency, such as 60 megahertz, and find all of the signals that way. Now, what we do, the modern day NMR technique, is to have a really strong magnet, and so that field strength is fixed, the B is fixed, it's held constant, and you listen by varying the frequency, you listen and try to find the signals by doing it in the neighborhood of whatever the spectrometer is. So if our instrument is a 300 megahertz spectrometer, it's stamped right on the instrument. We listen in the vicinity of that, and we will hear the protons resonate at that frequency near it, depending on the environment, of course, of the given proton. It could be a little bit less than 300, a little bit greater than 300. That's where we're getting the actual spectrum in terms of different peaks and different positions. So instruments are named in this field according to the resonance frequency of a naked proton. A proton without any electrons. So the frequency itself of the spectrometer, or the field strength of the instrument, is going to produce a slightly different position for the peaks. And so this is a problem, because we want to have an NMR spectrum be an NMR spectrum, right? We don't want it to be different on our instrument versus one at F&M or one out in California. We want, no matter what the strength of the magnet, we want the spectrum to look the same. And so the trick that we do is to scale the spectra. Here we see equation with delta. That's the chemical shift. That's the place in which the peak occurs. The chemical shift is defined as the difference in frequency between what we're measuring and a reference atom. In this case, we're using TMS, tetramethylsilane, that has carbons and hydrogens and silicon, so we can use it for those three atoms. If we're studying some other kind, if we're doing germanium NMR, we need a different reference, of course. But it's the difference between the signal we get and the reference signal scaled by or divided by, is what I mean, divided by the frequency of the spectrometer. And then since the numbers are very small, we just multiply by a million. And we call these units for chemical shift parts per million, simply because we're multiplying this by 10 to the 6. So here's a point where you can do a little exercise on your own. What is the field strength of our instrument? And what is the frequency range corresponding to a 10 parts per million window on our instrument? So you want to pause the video, try to work that out. Again, what we're trying to see here is, because we know our instrument is a 300 megahertz instrument, what's the B? What is the field strength of that? And that's the first question. In the second question is for a 10 parts per million window. So think of the shift as being 10 parts per million. Then what is the frequency range of that? So what would be the magnitude of what's in parentheses here for that case? Give that a shot and pause the video and then come back to check your answer. Okay, so here's what I computed for the instrument that we have in Campbell Hall. The magnetic field strength of our instrument is 7.05 Tesla. That comes about because we observe a naked proton at 300 megahertz. If we simply divide by the 7.623 in the formula, and then divide by also the G factor for a proton, we'll come up with the 7.05 Tesla. our field strength is at 7.05, although over time it's slowly disintegrating. So it's 7.049998 one day, and then 7.049997 the next day. It is deteriorating, and we account for that. The instrument mechanics account for that in the instrument measurement. Second question. Think now about a normal proton spectrum, right? It's a 10 parts per million window. Usually somewhere between 0 and 10 you find the protons on our instrument, or any instrument actually, because it's scaled, right? So what would that mean in terms of frequency range? So that if you fill in the numbers there, delta's 10, 300 times 10 to the 6 is the spectrometer frequency. So the 10 to the 6 cancels, and you get 300 times 10, or 3,000 hertz. So the magnitude that you're talking about in terms of the width of a typical spectrum on our instrument is the width is about 3,000 hertz. And so when you see splitting between peaks, like, typical triplet or doublet pattern, then that's on the order of magnitude of hertz. Next, I'd like to look at how you would compute chemical shifts in Gaussian, because this is going to be part of the lab exercise. And I think if I click on this will take me to, and you can do this too if you have the notes online. Hopefully this will take me to a WebMo summary, which shows you an example calculation that I've already done. Here's the molecule. It's TMS. So tetramethylsilane, you've got silicon at the center, and then 4 methyl groups attached to it. So this is a molecule that's used for reference in NMR because it's got carbon, it's got hydrogen, silicon, and it's a very shielded environment. That's going to put the raw shielding of this at a very high value, basically beyond what a typical carbon or hydrogen will see, so that the reference is out of the way of the other peaks that are seen in the spectrum. If you look at the raw output from a Gaussian calculation like this, we can see, it reports the energy and so forth. But there's a table here of absolute NMR shifts. I'm going to blow that up so you can see it a little better. It goes through and lists atom by atom what the isotropic shielding would be. And these numbers are for carbon and hydrogen are all almost identically equal to 0. That's because what we've done here to generate these numbers is to do a reference calculation on TMS and then store that in the program. So it's subtracting the TMS from TMS and getting 0. The reference values are shown here in the table. If you actually look at the raw output from Gaussian, you'll see that this, here I want to click on this. You can search for the NMR information by looking for ppm. There's only one place in the file that has ppm as units, and that's for the NMR output. And so if I go to that section and show you what it looks like, ppm, it has a list of atoms. They're numbered, so you know which atom is which. It has something called the isotropic shielding listed. Isotropic means averaged over all directions, and so this is what would be a typical NMR sample. Even though the magnetic field is vertical in the instrument, we're spinning the sample, and so the actual nuclei are seeing all random orientations of the magnetic field. And so Gaussian actually does compute the shift according to the different directions. That's what you see in this tensor matrix underneath. But if you want to simply simulate an NMR spectrum using Gaussian, it's the isotropic shielding value that's of significance. So here's what we call the raw shielding. We drew in TMS. We asked Gaussian to do an NMR calculation. That's all you have to do in addition to specifying the method in the basis set. You just say, I want NMR. And it does this calculation. The value is for the raw shielding. That's just a measure of how well the electrons are shielding that particular nucleus. So for carbon, it's 183. For a proton, it's around 32 parts per million. So these values are the raw shielding for a reference like TMS. If we were to calculate some other molecule, we would get a shielding that's probably less than these values because, as I said, TMS is an example of a highly shielded, they have nuclei that are highly shielded. And so your typical nucleus in some random sample is going to be less than this. So maybe for a proton, instead of 32, you might see something like 28. And then so the actual shift, it would be 32 minus 28. That's where it's actually going to show up in the spectrum itself. So when we do a Gaussian calculation, we have to take this isotropic value and then we have to subtract it from the reference value of TMS. And that's where we get those zeros that were reported in the summary table here. That subtraction has already taken place. That's why we see zero values for the carbons and the hydrogens here in the WebMO summary. So to sum up the simple equation for that, the chemical shift is calculated, if you're using Gaussian, from the raw shielding of the reference. That's what the sigma is here, the raw shielding of the reference, minus the raw shielding coming from the sample itself. And that difference then is the chemical shift that we would observe in the experiment. A lot of people want to subtract off the reference. Subtraction has to be done in this way, simply because the way someone a long time ago defined how an NMR spectrum looks. They decided that, we're going to put the highly shielded things to the right of the spectrum, and then moving to the left, we will see positive values for the shift. And if that's the case, and most atoms are less shielded, then we have to do the subtraction in this order. That is 30 minutes of a brief summary of the introduction here to NMR. We're going to do a lot more with Gaussian, so that was just an intro. We'll see a little bit more of how that works, and we'll talk about carbon NMR in the next segment. Thanks for listening. Talk to you later.